Thank you everyone for coming. Today we have as our speaker David Trestini, who did his PhD in Paris and did a postdoc in Prague. And now he's recently incorporated into the University of Southampton. And today he's here to tell us about his work on post-Newtonian results for compact binaries in GR and scalar-tensor theories. So, David, whenever you want, the floor is yours.
Thanks for inviting me to give a seminar here. It's a pleasure to be back in Lisbon. Last time I caught COVID in Aveiro, but so this time it's going much better. So I'll be basically giving you a talk about results I've been getting in the last 2 years, both during my thesis and postdoc last year, in collaboration with these people. And since today's October 31st, I have a few Halloween Easter eggs, so hopefully you'll find all of them. So the problem we're going to be interested in this talk is the two-body problem: two black holes, two compact objects, two neutron stars orbiting around each other. And this problem is typically divided into three phases: an in-spiral phase where the two objects are well separated or equivalently have small velocities or frequencies. This is the in-spiral phase we'll be interested in this talk, and we're going to basically expand in the small orbital frequency parameter. And then you have a merger phase, which is highly nonlinear, which requires numerical relativity. And then you have a ring-down phase, which can be either described with numerical relativity or perturbation. Then, of course, you have resummation methods, which allow you to try to get full waveforms in spiral merger. So really in this talk, we'll be focusing on this part here. And essentially what we want to do is we want to explore a certain parameter or corner of parameter space. So this will be, our dimensionless frequency parameter. So small frequencies, ISCO, large frequencies. This is our eccentricity, small eccentricities, separatrix between bound and unbound and large eccentricities, and the symmetric mass ratio. This is an equal mass binary, and this is extreme mass binary. And we're interested in this little corner of parameter space of small frequencies or velocities, small eccentricity, and comparable mass ratio. You have extreme mass ratios, we're in the realm of gravitational self-force. If you have an unbound system and weak fields, you have post-Newtonian. If you're strong fields and either small eccentricity or else scattering configurations, you get NR. And the goal of all these methods is to grow and cover the whole parameter space. So we're growing from this species. So what are post-Newtonian results used for? So both dynamics and waveforms, they can be used alone. So if you're thinking about LISA, for example, you can have binary systems which are actually in the weak field regime, which you can observe. And in that case, you're in the regime of validity of post-Newtonian, you can use the results. You can also resum them using Padé resummations to make them
more valid towards merger.
You can use them to inform effective one-body models, which have the same purpose. They enter phenomenological waveform models in spiral merger ring down, where you can hybridize them with NR and you can hybridize them with gravitational self-force. So this is really the bread and butter for everything which is weak field in very long times, which typically, for example, numerical relativity can't resolve. The advantages is that it's a first principle method. First of all, it's like ab initio, unlike resummations where you make some guesses. This is an actual prediction about the asymptotic properties of general relativity. It's fully analytical, fast to evaluate, and it in many cases helps us to understand physics in a way which you don't have an access to in other methods, because you actually have an analytical handle over things. But it has disadvantages, which is that it's only valid in the in-spiral phase. It tends to have a slow and oscillating convergence. I'll show you a plot where we see this, and it degrades for high eccentricity and mass ratios. So in the first half of the talk, I'll be presenting results I've got in GR. So I won't go into the details of how I derive them, but simply listing some results and the main takeaways from it. In the second part, I'll be focusing more on results I got in a particular scalar-tensor theory for eccentric or rather elliptic, quasi-elliptic orbits. I'll be delving a bit more into the technicalities in that second section. The recent results in post-Newtonian and GR. So typically the problem, when you're looking at post-Newtonian problem and trying to solve it, can divide it basically into three problems. The first problem is solving the conservative dynamics of your two-body system, which is trying to find the equations of motion, ignoring radiation and ignoring radiation reaction. So this can be done with a variety of methods, such as Fokker-Lagrangians, etc. And this will give you, for example, at lowest order, it will give you the integer Pn orders here for the acceleration between your two bodies, your relative acceleration. Once you've obtained at some order the conservative dynamics, you can then compute fluxes and infinity, exploiting the nonlinearities of propagation. And basically, at lowest order is the Einstein quadruple formula, and from your conservative dynamics, you can get radiation at infinity. And then this radiation back reacts, but you have a hierarchy. It back reacts at 2.5 post-Newtonian order, so 5th power of the velocity over the speed of light. And this gives us radiation reaction. So you see your leading order flux will lead to a 2.5 Pn correction in your acceleration, which is the leading order radiation reaction force. And so this is dissipative dynamics. And of course, these dissipative dynamics at higher order will re-enter the gravitational radiation. So you have to solve order by order iteratively, and this is constructive because of this hierarchy of scales between the conservative problem and the radiation. This is actually reminiscent of how we solve the problem, in the sense that we divide the problem into a near zone and a far zone. In the near zone, we obtain what we call a post-Newtonian expansion of the metric, where we expand in small velocities, or in large, formally we expand in the speed of light going to infinity. But then what happens is if you have a function of retarded time, so if you have, if you have like f of t minus r over c, well, if you tailor this, tailor expand this when c goes to infinity, we'll get f of t minus r over c f prime of t. And you can see very well that this blows up when r goes to infinity. So as soon as you have retardations in your problem, your post-Newtonian expansion breaks at large radii, typically at radii larger than a gravitational wavelength. Conversely, in Minkowskian, where you solve the field equations in vacuum, assuming that you have a small curvature. But this is not valid as soon as you have matter, so it gives you a solution, but it's not the correct solution. And since it's a multipolar expansion, it blows up when r goes to 0. Valid, and this allows us to proceed in asymptotic matching and formally say that the coefficients of the two re-expanded series are equal. And this effectively gives us a boundary condition between the near zone and far zone. And this is really reminiscent of this, hierarchy between conservative and dissipative. So I'll proceed to a quick review of the state of the art in general relativity. So the conservative dynamics. So everything here will be ignoring spin, because spins are a massive headache, whether they're aligned, misaligned. So ignoring spin. The state of the art for equations of motion is that the conservative equations of motion is the 4th post-Newtonian order, which was derived by different groups. So this is our group using Fokker-Lagrangian methods. You have the ADM so methods of Damour, Janowski, and Scheffer, which also obtained them first, then us. And EFT methods have also confirmed this effective field theory. At 5 Pn, these authors had claimed a full result, but it disagreed with the partial results of these people. Bini, Damour, CEICO, this is Blumlein, and other people, Schiffer here. And there's some recent results by Porto and then Fofa, which seems to start elucidating this problem. So the 5 Pn dynamics are close to being solved, I think, but it's not yet clear to me that it's actually the case. And 6 Pn only has partial results. Now, in the radiative sector, this is basically what I was doing my PhD on. So the energy and angular momentum fluxes. So if we look at the circular case, the energy flux, which is related to the angular momentum flux by a global factor, the energy flux was obtained at 4.5 pn order. Actually, the 4.5 pn order piece was obtained before the 4 pn one because it's easier. And so this was my thesis here. So in green, it's my paper essentially. And so here we obtained the 4 pn energy flux for circular orbits. It has not been confirmed by other groups yet. This 3 pn result was only confirmed this year by effective field theory methods, but it was derived like 10 years ago. So we still need confirmation of this result, but I mean, we're very confident. Now for elliptic orbits, we're still only at 3 pn order. Now that we have the radiation, we're interested in the radiation reaction, and this was part of what I've done last year. So the radiation reaction, the equations of motion, were known at 3.5 pn order by different groups. And at 4.5 pn order, you had these two results here, which claim to have it in the center of mass frame. But in the recent work that I'll be presenting as well, we've shown that these are actually incorrect because they basically do not account for a hereditary term in the passage to the center of mass frame arising specifically at this work. So saying that now we have state of the art is 4.5 pn here. So first result I want to present, which is the flux of energy at 4.5 pn order. Lo and behold, the big guy, but I'm not giving all the coefficients yet. No, so here, so this for notations, this m is the total mass of your two objects. Nu is the symmetric mass ratio. X is your frequency variable. At lowest order, if you just look at flux equals this thing here, this is the quadruple formula, Einstein's quadruple formula. And you can get a 1 pn correction to it, which reads like this. And so basically the lines here is, the powers of X will be the powers in your post-Newtonian expansion. And the diagrams I'm showing you, these are the nonlinearities in your far zone post-Minkowskian expansion. So I'm showing you the link between the two. And basically you can use linearized gravity up to 1 pn. But at 1.5 pn, you have the first nonlinear term that appears, which is the tail, which is basically your gravitational wave backscattering against the curvature of space-time generated by the binary. So it's a Coulomb interaction. So it's the interaction between your quadruple moment and the mass. At 2.5 pn, you have two quadruple moments which interact with each other, which leads to the memory effect. So you can imagine, two gravitational waves, and you have a beating effect. And so, you have plus frequency minus frequency equals zero frequency. That's how you get the DC effect. You also have oscillatory effects associated to it, but mostly known because of the DC non-oscillatory contribution. At 3 pn, you have tails of tails, so basically backscatters twice. And here you have lots of boring interactions. And my PhD work was mostly on these people here, which are cubic interactions, so spin mass quadruple interactions, and especially these tails of memory, which I'll be vaguely presenting in the next slides. Also at 4.5 pn, you have like tails of tails of tails, so basically iteratively this. The reason why these are more complicated is that you have two dynamical moments, whereas the mass is constant. So you have to, you have these integrals with these two dynamical moments, and it's cubic. So that's what makes the computation more difficult. So how can you see this another way? Basically, these propagation effects, we account for them by relating two types of multipolar moments. You have the canonical moments, which basically account for what's happening in the near zone. How do you have your binary, and these are given in terms of the binary variables. And then you have the radiative moments, which describe your field at infinity. And in between, you have some propagation effects. And this is what we're trying to describe by relating the radiative moments to the canonical moments. So at leading order is the same thing up to time derivatives. And then you have nonlinear interactions that pop up. And so these were the tail of memory interactions. And maybe to just in one slide show you what they are, you take tails, you take memory, put them together, you get tails of memory. So once we get this flux at infinity at 4.5 pn, yes? You mean these nonlinearities?
Yeah.
The thing, for or not for, you detect them in any case. It's just subleading in the post-Newtonian order. So depending on how accurate you have your waveform, you'll detect them more or less. But what I'm stressing is that they really appear in the 1/r piece of the waveform, in the asymptotic waveform. So it's nonlinear. It's basically, what happens is that it's near the source that all the nonlinearities happen in the strong field regime. And the imprints of this are propagated to infinity. So once we have the flux at infinity, why are we interested in knowing the energy flux in the first place? Because we also know the energy, the conservative energy of your binary. And we can write down this postulate a flux balance law. So here it's just a postulate. I'll show some proofs at lower order later. But if we postulate that basically energy is conserved in some sense, we can write down d over dt equals minus the flux. Up to some subtleties, which are that the energy is expressed in terms of an orbital frequency, which is defined for the conservative problem, whereas the flux is expressed in terms of the waveform frequency at infinity. So you have to have some postulates you have to make in this, but I won't discuss it here. You can basically write this down and recast it, and with some very basic manipulations, you'll find a differential equation for the frequency of your gravitational wave at infinity. This is the chirp, which is the main observable. So basically getting the flux and energy gives you the main observable of a gravitational wave at infinity. And integrating this will give you the phasing. So this is the result. We have the phasing ready for gravitational wave detectors. So this is a recent result, and there is a tiny bit less recent result, which was the fluxes at infinity at second order in the mass ratio expansion. So instead of expanding in small velocities, you consider, for example, an extreme mass ratio system, and you expand in the mass ratio. At leading order, this was known for a long time, but there's a recent result by the group in Southampton that found this at second order. So if you write the flux, this is again your quadruple formula. This is the leading first self-force and second order self-force results. The first order self-force, we actually know how to expand this analytically as a post-Newtonian expansion. And all these crazy coefficients, these fractions, they all agree identically between our methods and their methods. So this is already, our result agrees with them. For the second order results, it was obtained numerically, and I'll be showing that we find good agreement with them. So this is the first plot where I'm showing the second order piece of the flux. The dotted line is the self-force result, and here are the post-Newtonian results. So at 1 pn, you see it's performing moderately bad. So to show you the oscillatory behavior of the pn expansion, at 2 pn, you see that it's performing much, much worse. And then with 2.5 pn, it goes back, it performs very well, then it goes back down, up. But the two green curves are 4 and 4.5 pn order, which are, it's starting to get very close. So globally, it agrees well, but we wanted to check coefficient by coefficient. So what we've done is that first we plot the self-force and pn curves. They agree very well here. And then you look at the residuals. So you subtract the 3.5 pn piece from the self-force and from the 4.5 pn. And you see that asymptotically, it's the same slopes here in the weak field regime where we expect them to agree. And as you go down, what you find that everything is consistent, although the self-force now has lots of numerical noise in this region. So we can't claim, perfect agreement or anything, but at least here it's all noise, and you're starting to see some asymptotics which are compatible. And also importantly, if you compare to numerical relativity, at first order the self-force, both in the post-Newtonian expansion or just self-force expansion, for an equal mass binary, it performs very badly. Equal mass binary, you're not expecting self-force to work well. But if you go to second order self-force, then both actually perform relatively well up to some very high, large frequencies here. So just as a reminder here, the frequency of the ISCO in this a-dimensionalized definition is 1/6. So we're really we're right near the ISCO where everything is supposed to break down anyway. And yes, so here, and you see that they both agree but go in different directions compared to NR. Another interesting feature is that although we agree very well on the total flux, if you decompose the flux mode by mode in spherical harmonics, then mode by mode, we actually get pretty stark disagreements, as you can see here. And if you sum it all together, suddenly it magically agrees. And this is basically, this indicates that we have mode mixing, and that probably we're not in the same frame. We're not in the same center. The self-force computation is probably not in the center of mass frame. So this led them to start, the self-force group, it led them to start looking into what exactly is the frame they're in and try to go to the real center of mass frame to see if we agree then mode by mode. Right. So now this was for the fluxes in the radiative sector. Now I'll be discussing the work in the radiation reaction sector. So we're going now back to the equations of motion, back to the near zone. And basically the acceleration is given, by Newton's law, plus Pn corrections, which are conservative here. And the first radiation reaction piece enters 2.5 Pn. And I'll be presenting results at 2.5, 3.5, and 4.5 Pn order. Note that at 4 Pn, you have both conservative and dissipative effects, but these are well known, so I won't be discussing them. So what we obtained was the accelerations of each particle in terms of the multipolar moments, the canonical moments. This arises from the matching procedure I've described to you. So I'm not, there's no point in showing this very long result, but it's important to have it expressed in terms of the multipolar moments because, as I'll show in the next slide, this was very useful in showing that you have the flux balance laws, which are obeyed. So it was very useful to keep it in this form. But then, of course, we can replace these multipolar moments by their expressions, which are well known in terms of the positions and velocities of each object, and take time derivatives using the equation of motion. And basically, we can get all of these, fully explicitly. It's just horrible. So interesting verification, once we've obtained these equations of motion, was to prove the flux balance laws at 2 Pn. So I've told you that you had subtleties about how to relate the far zone and the near zone, so the flux balance laws are a postulate, but we can prove them explicitly at the finite order we're working at if we have both the energy and equations of motion and fluxes computed at that order. So what we did is that since we know the energy, so you have 10 Poincare invariants, which are the energy, angular momentum, linear momentum, and center of mass position, which all obey these flux balance laws here, which are related to fluxes in infinity, which we have also computed at the right order. Note that the center of mass also has a flux associated as well as the linear momentum. This is something which is not necessarily wrong. And what we found is that we can find some quantities which satisfy this. And in practice, what we've done is that we took the conservative energy, angular momentum, etc., which are zero if you take their time derivative with respect to the conservative acceleration. But if you take the time derivative with respect to the full dissipative acceleration, it's non-zero. So you take this, you add the flux that you expect to see at infinity, and then you say, oh, we want it to be zero. But in fact, no, it's not zero. You get an expression. But we've been able to show for all of these that this expression is in fact a total derivative. So this is what we call a shot term. And this is basically a redefinition of your conserved quantities, which were defined in the conservative problem. Now they're redefined in the full problem, but at least you can find a total derivative for this expression. This is not highly non-trivial, and this is basically the proof of these flux balance laws. So if we now look only at the flux balance laws for linear momentum and center of mass position, we can integrate them. We get expressions which look like this. And then there's a subtlety in how you define the center of mass frame. We want an inertial frame, and we want to say is that initially at basically a very, very remote time t0, before there was any emission, we want to be in the center of mass frame. We want to have P0 and GI0 equals 0. And this leads to the condition to be in the inertial frame that we have this G quantity, which was supposed to represent our center of mass position in the conservative problem, was not G equals 0, but G plus gamma equals 0, where gamma is an integral over the fluxes at infinity. Basically, what we're saying is that the inertial frame is not frame centered around the matter content, but you have it's the barycenter of both the matter content and the flux escaping at infinity. This is how our these non-local terms arise. So it's very linked to the recoil, the gravitational kick. So if you have a circular orbit of asymmetric binaries, your center of mass position will go around like this. And if you have an elliptic orbit, you're going to be emitting more gravitational waves in one direction than the other. And so basically, here I'm showing basically the little graph in the center of mass frame, and you have the binary which is getting kicked in one direction because you have gravitational waves being sent in the other one. And if you don't work in the inertial frame, you lose, basically all your flux balance laws just don't work. So you really need to be in an inertial frame. So we take now, once that we know that this is the right condition, we can obtain from it the passage to any, so we were working in a general frame. We have the positions of particle 1, 2, etc. And we want a recipe to express the position of this particle 1 in terms of the variables of the center of mass frame. Historically, the recipe was given like this without this R term. And now we have to add this term here, which is the contribution of the radiation, which reads like this in terms of this gamma integral I've shown you before, which keeps, it's a hereditary integral depending on the whole path of the binary, keeping track of the fluxes and infinities. And then once we have that, we can now take our 4.5 pn acceleration, express it in the center of mass frame, and we get this extra non-hereditary contribution in the acceleration, which arrives as basically from this gamma term here. Pi is essentially the time derivative of gamma that it comes with. Right, so we get this expression in the center of mass frame. All our flux balance laws are still satisfied, whereas if we had ignored this non-local term, they would not be satisfied anymore. And we wanted to compare to the literature, and we don't agree because they don't have this non-local term. The reason for the first paper is that they just took an ansatz for the acceleration. They've worked in the center of mass frame, took an ansatz which is dimensionally meaningful, but they didn't account for the possibility of hereditary terms. And the second paper, they normally did it from first principles, but they set gi equals 0 rather than gi plus gamma I equals 0, so they got a wrong result. So that's kind of the conclusion. And maybe I'll take questions now about the GR part before I go to scalar-tensor theory, if anyone has some.
Who is they? Last two results.
This is Gopakumar Ayer, and this is Leibovitz and other people. So this is EFT methods. Yeah. Yeah.
It was found like the last year, there was 2.5 was at the date of 2016.
Yeah.
I don't know why.
Because it's a very different computation to be done for integer powers and odd powers, and it so happened that the group was able to get the 4.5 pn piece and arguments, basically get that piece before they got the 4 pn piece. So as soon as we got the 4 pn, we automatically got the full 4.5. That's why. Yeah. No, go ahead.
So the was showing like the memory, like the last line.
Yeah.
One of them had like binary.
Yes. So it's actually abusive language.
Yeah.
So I said spin because it's quicker, but it's angular momentum. This SI is the ADM. It's the angular momentum of your space-time, which is conserved. So it's basically it's backscattering against the mass and the angular momentum. It's not the spin of the particles.
But at what order would the spin of the particles enter in these expansions?
I think it's in the waveform. I think it starts 1.5. If I'm correct. I never worked on spin, so I think it's 1.5 in the fluxes here, but in this expansion it wouldn't enter because this is like the spins of each particle would be within the multipolar moments, basically. So they modify the definitions of the multipolar moments, but these things are kind of generic for instance. This is how you replace them in terms of the source variables, which is going to change.
mentioned that some force people would now like to try and do calculations in the center of mass frame, because that might make
Yeah.
it easier
Yeah.
to compare with.
They kind of want to
With both
control
of
the
them.
frame they're in.
Yeah.
Yeah.
Right. Okay. I'm wondering, like, is there an advantage to doing that besides the PN comparison? Like, is there, like, from a purely self-force point of view, is there any
Well,
other motivation to do it?
I think there wasn't until now, and that's why they haven't. Nonetheless, I think if you want to give a, since the gravitational wave you're going to observe is going to differ depending on, if the system is boosted or not compared to you and what frame you are in, there's value in knowing in which frame you are giving the results. Historically, the thing with self-force is that the frame is just the frame of the center black hole. You have a big black hole and a small particle. So at leading order, center of mass frame is the frame of the big black hole. But now if you add a second particle and go next to order in the mass ratio, how do you define the center of mass? It's not clear. So it's work ongoing on that. Yeah. Yeah, no.
So for something that with frames in the mass frame, because I read in the way that we did in science fiction and relativity, but if you compare to the experiments, what is the fact to say like what they call the BMS frame?
Yeah.
So that is related. Is that transformation on top of the center of mass?
BMS is, so basically BMS frame is, if you're looking at purely asymptotically, you have a lot more symmetries. So there's certain ways to fix this. So just being in the center of mass frame is like a poor man's version of fixing the BMS frame. Nonetheless, like for the fluxes, you don't expect it's invariant. I think we expect it to be invariant in different BMS frames. Well, to be seen, but yeah, it's related. But BMS is an extension of the frame you can be in. Great. Okay, so now I'll be talking about some results in another theory. So you had is there a question or just on? Okay. So in another theory, which is scalar-tensor theory. So essentially, what is scalar-tensor theory? You take the action of GR, but you multiply a scalar field with the Ricci, so non-minimal coupling. You endow the scalar field with a kinetic term, and for simplicity, we do not give it a mass. We do not give it a potential. That's the action. That's the field action, but you have the matter part of the action, which is a point particle action for two particles, except that we have to make the masses of each particle dependent on the scalar field. So initially, if you look at the action here, it's what we call the Jordan frame because the matter action does not depend on the scalar field. But now if we take the effective action where we're integrating out, we're taking the effective point particle limit, then you'll find that the effective inertial mass of your neutron star will depend on the local value of the scalar field. And so you have to, this is found by Erdely, and you have to, endow your masses with scalar field, and that's a breaking of the weak equivalence principle. So this is how we formulate the theory, but it's not how we compute it. We like to go in what we call the Einstein frame by doing a conformal transformation, such that the equations that we solve resemble the ones in GR, and we can, reuse all the techniques that we've developed for GR. So these are our little perturbation variables, but you have to remember you just have like a tensor and a scalar perturbation. So what we also do, since we're doing a post-Newtonian expansion, arbitrary function that we've chosen, well, we do a post-Newtonian expansion of it with coefficients. We expand the masses as well in terms of these sensitivities. If you have a weakly gravitating star, the sensitivity is going to be very small. If there's a neutron star, it can get larger, it can be 0.2. And through Noether theorems, we can show that black hole sensitivities are exactly one half, which is means that you have a scalar charge of 0. And essentially, in scalar-tensor theories, if you have two black holes, you recover exactly GR results. So you need to have at least one neutron star in order to have deviations. And if you ever see some ugly parameters, then these are basically combinations of these guys. So ignore them. Okay, this is a special slide for David. Why in the hell do we study these theories in the first place? The usual thing, the naive.
Let's get exactly like that.
No, oh no, my Easter egg is It's hidden. Okay. So yeah. So the naive answer would be, oh, we want to look for deviations for GR, so we're relating this theory and hoping to find deviations. Actually, not really, because this was actually the work of D'Amour Esposito Fares, who first formulated these and studied these, and later on Freire, etc. But basically, binary neutron star constraints are extremely stringent for these theories, as well as solar system tests. So what do we study now? Well, the first one is that it's the simplest motivated deviation to GR. You just take GR, add a scalar field. And we don't really know how to create, basically if you, Lovelock's theorem, if you want to alternate theory, you have to add some extra degree of freedom. Second, the technology we're developing for these things is actually useful for more complicated theories, which can be less constrained. So there's been recent work, for example, with scalar Gauss-Bonnet, where basically scalar Gauss-Bonnet is the same results as scalar-tensor at 2pn. You have deviations at higher order. But the difference is that due to strong field things, it's a contrary for the sensitivity. So black holes are scalarized, but not neutron stars. So that means you're going to get constraints from gravitational wave observations of two black holes, but binary neutron stars will not give you any constraints. So this is just an example, but you can imagine screening, you can imagine lots of things where we could reuse this technology and adapt it to these new theories. So it's important to start with the easiest thing because it's hard enough as it is. Also, we've been looking for gravitational waves using GR templates, and we said everything that we've detected is compatible with GR. But since we're looking with GR templates, maybe there's something very exotic that we've missed, and so maybe these templates can be useful for searches, even though it's not the actual theory. Maybe it's close enough, useful to use. And finally, I'd like to argue that it's a very good toy model for studying GR. Because dipolar radiation is easier than quadrupolar radiation, as we'll see in the slide later. And there's no gauge problems with a scalar field. Right. So quick backtrack to beginning of my thesis, where I got some results with Luc and Laura Bernard, who was here for a postdoc quite a few years ago now. Essentially, what we got was the gravitational wave phasing, as I presented for GR. For circular orbits at 1.5 post-Newtonian order. So that's 2.5 orders beyond the leading order. Because in scalar-tensor theories, basically, the leading order is a -1 pn dipolar effect. So you have a scalar dipole, so it's like promoted by one order. And the counting that we usually do is with respect to GR. So that's why we say it's a 1.5 pn expression, but it's actually relative 2.5 pn in terms of computational difficulty. And recently, there has been some numerical simulations by Sujung Ma, Vijay Verma, Leo Stein, and other people. Basically, they use I think it was Spectre, full hydrodynamics for the neutron stars, maximizes spontaneous scalarization, whatever. And they're in pretty good results. So in green is the NR curve, and in purple is our predictions, and they're in pretty good, agreement. You have a little discrepancy here, but actually, if you chuck the highest pn order, you recover agreement. So you can imagine that it's this oscillatory, pn behavior where you add a half order will be good again, and it even works well for the DC memory effect. So that was pretty nice. And now what I want to be talking about is some extensions I've been doing this year. Yes. So it's alternative current, direct current, but it's basically non-oscillatory effects, like the memory effect. So, and I want to talk about now results I've done extending this work, but to eccentric orbits. So the first part of studying eccentric orbits is studying eccentric motion using what we call the quasi-Keplerian parametrization. So the starting point is basically Newton's law of gravitation, once again, where this G effective will be different in GR and in scalar tensor theories, but who cares? It's a constant. And if your relative acceleration is given like this, we know that the motion is an ellipse, right? So this is the trajectory of the particles. It's an ellipse described in terms of the semi-major axis and eccentricity, which are given in terms of the energy and angular momentum of your system. Okay.
So before you go on, you're claiming this, but you still have a generic omega t, right? Like putting like a Newtonian limit in your scalar-tensor theories doesn't constrain the functional form of the coupling with the scalar or something. Like, would you claim whatever you put in the scalar part recovers a Newtonian limit?
Yeah, so at least in this theory, yes. So basically you get like you get your omega 0, etc. They renormalize your G function at lowest order.
Okay.
Like you have a, yeah, it's an effective G. I mean, otherwise the theory would have been even more Rupert. But yeah, so
Yeah, but like it seems that you were putting like something completely general, right? That's why that's
no. This is I mean, this is the theory we're looking at this theory here, right? So it's not completely general. It's a theory. If you have Yukawa things, you're gonna have exponentials, but we don't. So yes, for things. So yeah, so here this is our acceleration, and we get an ellipse. But actually, we're interested in having a parameter, an affine parametrization for your motion. And it so happens that the simplest thing is not to express everything in terms of time, but to express everything in terms of what we call the eccentric anomaly, which will be denoting u. And we can express, this is going to be our affine parameter, and we can express the radius, the separation between the two particles, time, this L, which is the mean anomaly, and your angle of your motion, polar angle or whatever, in terms of this eccentric anomaly. You also have this true anomaly, which is related to it like this, and more quadratic corrections and hierarchy. So this is nonsense like Kepler, basically. And the second equation is what we call the Kepler equation, relating the time to the eccentric anomaly. And inverting this is actually like it's a transcendental equation. So, there's lots of problems in Newtonian mechanics for this. Just this is a little plot. So this is your binary. This would be your eccentric anomaly. It would be defined like this, and this is your true anomaly. So the question is how, now if you take the 1pn equation of motion, so you include 1pn corrections, what would be the solution to this? And so this was found by Damour de Ruel, what they call the quasi-Keplerian parametrization. And basically you're modifying your parametrization I've shown you before by adding this k, which is the pericenter precession, lifting the degeneracy between the eccentricity. So you have a different eccentricity for each equation. And your parameters, for example, your period gets a bit modified. So here, I've heard that this logo is now outdated, but I had another plan to replace it. And so basically the time, now that you have precession, the time between two periastrons is what we call the radial period P. And this is different between, the time it takes to go from, for your angle to go between 0 and 2 pi. This would be omega, which is n times k. So this, is basically, we have a double periodic motion and due to the precession. And now if you go to 2pn order, this in GR, this was shown by Damour and Schiffer, that you can further modify your parameterization by adding these extra terms here. Okay, so this is the whole parameterization we have in GR. And we didn't have this in scalar-tensor theory, so the first part of the work I've done was to extend this to scalar-tensor theory, and actually even more generic theories, as I'll show you. So how do you do this? What you do is that you take your quasi-Keplerian. So how do you determine the expressions of these parameters, although these quasi-Keplerian parameters in terms of only the energy and angular momentum? That's the goal. But what you do is that basically within the post-Newtonian theory, you found an expression for a conserved energy and conserved angular momentum, which is basically a complicated combination of your positions and velocities. Okay. And these equations, this is post-Newtonian, you can invert them in a post-Newtonian sense, and you can obtain basically the r dot, or like the change in the radius and the change in the angle in terms of the radius r and the energy and angular momentum. You're inverting this, and what you'll find is that at 2pn you'll get a polynomial structure like this, where A, B, C will be enter at Newtonian order. D1 will be a 1pn quantity, so it drops out at Newtonian order of 1pn, etc. So you have like a hierarchy in these things. And actually, this structure, you'll find it in GR, in scalar-tensor theory, and I'd like to argue you'd find it in many other theories, which will have, basically different expressions for these coefficients in terms of energy and angular momentum, but nonetheless, the structure will always be like this. And so I've tried to basically get, work keeping this A, B, C, etc. As generic as possible, because then you can plug in the results for any other theory you're interested in. And so, for example, things we obtain is that would be your semi-major axis expressed in terms of these ABCs. And if you replace these ABCs by their value in scalar tensor theory, well, you'll get something like this. This would be your normalized energy and normalized angular momentum. But so this was very useful for my calculation I'll be showing later. But I also want to argue that if you now have a favorite theory and you can determine in a post-Newtonian sense this and invert it, so the inversion process is extremely easy. It's just determining this, which is a bit harder. Once you've done that, with this result, you immediately have your quasi-Keplerian parametrization by plugging in the values of ABC. So hopefully, anyone's doing these theories, you can use this. Right. So now we're now interested in using this for looking at the radiation and the radiation reaction. And in general relativity, you have I think Matthew Peters, who obtained a very interesting formula. So basically, he takes the Einstein quadruple formula, but for energy and angular momentum, and elliptic orbit, and just postulates, conservation of energy and angular momentum, Buck-Bannis laws. And he basically found that this would lead to a relation between the semi-major axis and eccentricity, which reads like this. This is a secular relation, so ignoring small oscillations. Basically, if you start off with a binary which has a semi-major axis A and E, and let it evolve under radiation reaction, the parameters of your orbit are slowly going to change. And they're going to change according to this law, where C0 is a constant. And I found that in scalar tensor theory, you can do the same thing, but use it with a -1 PN dipole radiation instead. So these are, your dipolar fluxes here in terms of the source moments, blah, blah, blah. And I get in scalar tensor theory, I get a relation which is like this. So you can see this relation is much, much easier than this one. And this will be useful because we can use later on these relations and integrals to perform integrals. And this is in the sense in which I was saying that scalar tensor theory can be a good toy model, because this is much easier than this. This will give you, when you try to integrate these things, you're going to get hypergeometric functions, whereas here you get arctan. So, right. And remarkably, this relation does not depend on any scalar tensor parameter. Yes? So, yeah, good question. So this was determined within scalar tensor theory. So that's how I got it. And what I find is that it doesn't depend on the specific parameters of the theory. Now, I can imagine that if you take another theory with a scalar field, I think you would get something like this as well. But I haven't proven it. But yes, I think it's basically generic to the presence of dipolar radiation. So this is how the two curves look. If you basically, in the infinite past, you basically take the same binary, the infinite past, you'll see that they'll evolve differently. But do note that we don't have the time evolution on these curves for either. So we don't know which one, it's not clear which one circularizes the fastest. It depends on what region you are in parameter space. Just in the passing, using the quasi-Keplerian parametrization, I was able to obtain at some low Newtonian order, so that's relative 1 PN, the amplitudes of your gravitational wave and scalar field. So this is kind of what I've showed you before for circular orbits, how the amplitudes, well, I get something similar, and these amplitudes oscillate on the period with the orbital period. But now what I want to show you really is just a recent paper which came out maybe a week ago or two, where I used this quasi-Keplerian parametrization to obtain the fluxes of energy and angular momentum at 1.5 post-Newtonian order, which is basically the same order as we obtained for circular orbits. Yeah. So in this computation, you have quite a few subtleties, because the flux, so you have your total flux of energy, which I call F, and of angular momentum, which I'm going to call G. So you have a tensor sector and you have a scalar sector. And in the computation of these, you have some nonlinear effects that appear. You have tails. So I've shown you all these in the concept of GR. So it's essentially the same thing, but with different moments, like scalar dipole moments, basically. You have tails that appear, quite a few tails. You have a memory term. You have lots of boring instantaneous terms I'm not going to be discussing. And you have very interesting new hereditary terms, which arise from the non-local part of the passage to the center of mass frame. So what I've shown you in GR, which appeared, this non-local contribution to the passage of the center of mass frame, this appears at lower order in scalar tensor theory. And since the dipole has a different structure than a quadruple, this promotes it even to lower order. So we're going to have these things appearing in the waveforms at much, much lower order than we do in GR. In GR, it would be at 5.5 pn. Here it's at 3.5 pn. So I'm basically going to be discussing the last of the talk is kind of how do you deal with all these different terms in the context of eccentric orbits? And the techniques I'm going to be discussing are basically the same techniques as you would use in GR. Basically the bread and butter to do this is to perform the Fourier, the expansion of the multipolar moments as a Fourier series. If you take a multipolar moment at Newtonian lowest order, it's perfectly periodic, right? There's only one period. And so you can write it down, you can decompose it as a Fourier series in time, where your Fourier coefficients are given as usual. And you can, basically, if you change variables from time to go to this eccentric anomaly, which is our preferred affine parameter, you'll basically find that all these guys can be expressed in terms of Bessel functions. This is the kind of thing that appears. So for example, for the dipole, so simply for the x, y, and z, if you have an ellipse which is like this, okay, this would be the x-axis, this would be the y-axis, z. So you can decompose it on these axes, and you'll find something like this. So your piece scalar dipole in x will be Bessel function like this, etc. So at 1 pn order, you have something interesting that happens, which is yes. 5 minutes, okay. So you have something interesting that happens, which is that you basically have a double periodic motion. And so you have to decompose it into these two periods. But then essentially you have the same procedure. You can get something like this, and you have to introduce these new special functions, which are horrible, but which exist. And so now if you want to compute the tail integral, so what are tails? Tails are basically non-local integrals of your multipolar moment times a logarithmic kernel. And so we know how to do this very well in circular orbits, thanks to formulae like this one. This is, we can perform this. But basically, since we've done the Fourier decomposition, it's, basically, how do you call apple cycles? I forgot how you call these things, but in Newton, before they found it was an ellipse, they would do lots of little circles. Someone knows the name of this. Epicycles, that's it. So basically, you just, once you've done your Fourier decomposition, you can basically plug this, use this formula, and you get an expression. So typically, the type of expression you get for your orbit averaged fluxes, the tail piece, would be something like this. So you have some prefactor, blah, 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 times a function like this of x. This is a pure function of eccentricity, which we call an enhancement function, which can be expressed exactly in terms of infinite sums over our multipolar moments, of which we have expressions. So this is a solution, but it's not very elegant. But we can either compute these numerically, or we can perform small eccentricity expansions like this and resum them, etc. So these are known, but unfortunately, we have to have these arbitrary functions, these functions which are not expressed in very good closed form in the expression of our tail fluxes. You also have the memory contribution to the flux. So a memory term is a non-local integral of two multipolar moments beating against each other. So I'll project this onto the xy axis here. So you get an expression like this with your integrating functions f and g, which are products of moments like this. And so we're calling this Fourier expansion of the dipole. So using the Fourier expansion, you basically replace these by the Fourier expansions. And this allows you to separate these functions into orbit averaged DC non-oscillatory part and a purely oscillatory zero average part. So F orbit average and F tilde. And this F tilde can basically be expressed as sums over the Fourier coefficients. The AC part is very easy to deal with. So you have an AC part of the memory angular momentum flux. So you write this down and you perform your integrals and you get an expression and you find that after orbit averaging it's 0. But the problem is that if you plug in your, if you had kept the DC terms, you would find that these integrals would be permanently divergent. This is because the DC terms, their time dependence is not in the fast oscillations, but in the secular evolutions of the orbital parameters. So for the DC terms, what we do is that we define this DC part of the memory with these F orbit average and G orbit average. And we compute first the orbit average explicitly in terms of original multipolar moments before performing the Fourier decomposition. F average is 0, and G can be expressed in terms of the eccentricity and semi-major axis like this. And this is the moment where this Peters formula I've shown you before is useful, because then, so I also derived this, I didn't show it, but you have basically an evolution equation for d over dt and a relation between A and E. So in this integral here, you basically replace everything, and you can replace your time integral of your secular things as an integral over the eccentricity. So you just do a change of variables. And so if you go in the, so since your orbit has a tendency to circularize, so if you go towards the future, your eccentricity goes to 0. And if you go in the past, because you're integrating over the past, your eccentricity goes to 1. And so you have an integral going, with a bound of eccentricity today to eccentricity 1. And so this is important. In GR, it was found initially in this paper that the DC contribution behaves like diverges in the initial eccentricity. So if the initial eccentricity goes to 1, your DC contribution blows up, which is kind of weird, right? And so here in scalar-tensor theory, I found no, everything's quite convergent. And I get a result which looks like this. And this is a finite result. And if I orbit average, it's 0. And I've actually redone, and this is the appendix of the paper, I've redone that computation in GR and found that it's the same in GR. Everything converges, except that instead of having this very nice expression here in scalar-tensor theory, you get something in terms of like hypergeometric functions, which is absolutely horrible, but it's all convergent. And this is kind of to go with the thing I was arguing that, studying these theories allows us to understand GR better. And actually, the reason why this was incorrect is that they hadn't done a good split between AC and DC terms. They had expanded in phi, the angular variable, and basically said that the m equals 0 term in that expansion of the DC term, while it should be the m equals 0 term in the time Fourier expansion. So that was the origin of the problem. Finally, very quickly, you remember this was what we had in GR. We have the same thing in scalar-tensor theory. To go to the center of mass frame, you have a non-local term. And this non-local term, basically will enter the source dipole moment and give a non-local term to your instantaneous action, basically, in the center of mass frame. But using the same Fourier techniques I've discussed, you can show that this averages to 0. So you can ignore it in the end, at least at the orbit average level. This is not what I want to show. And finally, so this is kind of the fluxes we obtain at a lower order, and you get corrections to this. And same as we've had in GR, we can basically use these fluxes, add the energy to get the most important result, which is the secular evolution of the orbital parameters. So if you write this orbital parameter x, which can be the frequency or eccentricity or anything else, well, we do like this chain rule. Since we had the quasi-Keplerian parameterization at first, this guy we know. So we can obtain these we obtain for the quasi-Keplerian parameterizations. And these guys are basically the fluxes, which we've just obtained. We do everything. And we have basically, this is the structure of the evolution of the frequency and eccentricity in terms of the frequency and the eccentricity. So these are differential ODEs you can solve numerically with lots of coefficients, x4, x5, and E1 here, etc. So hopefully now this is also for David. You're ready for some Halloween horror. This is an expression of one of the coefficients. So yeah, half of the paper are appendices, as you can imagine. And so now I think I'm over time, so I'll just leave you with the conclusions of everything we've gone over and take questions.
We are a bit over time, but if anyone has one or two quick questions, feel free.
Around page 40, you're describing how you could invert in a post-Newtonian sense a certain expression, and you get these or something that looks like an expansion.
Yeah.
On it, right? And then here you say on the side for many theories of gravity. I wonder, are you hedging your bets there? Like, do you think that there are counterexamples? And if so, like structurally, what is the requirement on the action on the field equations?
I don't know the requirements on the action. What I can say is that this, even within scalar tensor theory, this will break down in the next order because of what's written here, but I didn't say. Basically, the structure, it breaks down as soon as you have tails, right? So in GR, you have tails at 4pn. In scalar tensor, they're at 3pn. So as soon as you have tails, you don't have a polynomial in R, you get have something which is hereditary. So, but I don't have any constraint on the action, but it's intuitively, I would say that if you take scalar Gauss-Bonnet or something kind of which is not too exotic, at least to the lowest orders, you will have polynomial expansion like this. This is what I would expect. So if in your theory you can write it down like this, then you can use these results.
If you enjoyed the video, like and subscribe.